Hello everyone, welcome to the 11th interaction session of Fundamentals of Electrical Engineering. I'm your TA Dipanita. This week sir has taught about the transformer, single phase transformer and about the three-phase induction motor. So we'll be solving a few problems regarding efficiency of the transformer and a few basic problems of induction motor. So let's look into our first problem. So here it is given the efficiency of a 20, this is the rated uh, power of the transformer 20 kVA with the high voltage side and the low voltage side voltage are given, and it is said that it has unity power factor, that is cos phi is equal to 1. The efficiency at the rated load is 98%. Similarly, at half rated load, it is still 98%. We have to determine the percentage equivalent resistance of the transformer. So, how are we going to solve this problem? So, in case of a transformer, like in case of any machine or any instrument, the efficiency is given by the power output by the power input. In case of transformer, it is uh, like the power, that is the output power by input power plus losses, because there are, as we have seen, this loss consists of the copper loss and the iron
Core loss.
loss, right? Core losses. So in order to incorporate the load at which the transformer is performing, we have the formula of efficiency as X. This X denotes the fraction of load that is getting used. So this into whatever the rating will be there for the transformer, let's consider this to be P cos of phi, since this is given in kilovolt ampere, right? So we need the power output, so we are multiplying with cos phi. So we will get it in kilowatt by x p cos phi plus the losses. So in case of iron loss, it is constant. So we will write it as a constant term. However, the copper loss is basically I square R loss. So if the transformer is not performing at the rated current, so it should be the fraction of the rated load at which the transformer is working times R. So it will be x square, and let's denote this I square R, like this will be x square I square R, right? This is the copper loss, so let's denote this by WCU. So we are going to use this formula in order to extract the losses, so that we can determine in order to determine the percentage equivalent resistance. So for the first case, when efficiency is equal to 98% and it is working at the rated load, that is full load. So it will be given by, if we just simply use this particular formula, it will be 0.98 is equal to x, here is 1 since it is at full
1,
load. What is the value of P?
20 kVA.
Right.
20.
So let us just write 20, and we will calculate all of this in form of kilo, like in terms of 10 to the power 3. So we'll just write here 20 and cos phi. So it is given unity power factor.
1.
So it is 1. Similarly, so this is 1 into 20 into 1. And these are unknown quantities. So let us just write it as it is. X is 1, so 1 square into WCU. So we'll just rearrange this, take this on this side. So it will be 20 plus W. This is the iron loss, this is the copper loss. It is equal to 20 divided by 0.98. So we will get one equation as Wi plus WCU equal to, so 20 divided by 0.98 is 20.408.
20.408.
Yeah, so minus 20. We'll bring this 20 on that side. So it is
4, 8.
0.40816. This is one equation we have. So we basically need to calculate this copper loss so that we can get to the percentage equivalent resistance, because the copper loss incorporates R, and rest of the things are not given here, so we need to calculate it. So the other equation that we will be getting is from the next part of the question which is given. It still has an efficiency of 0.98 at half the rated load. Half the rated load means x equal to half.
1 by 2.
Right. So again for the next equation we have 0.98 is equal to zero point 0.5 times P is 20 kilovolt ampere, cos phi is 1, 0.5, 21. The iron loss will be same, only the copper loss will now change. It will be 0.5 square,
Yeah.
right? So let's take this, let's rearrange this properly. So it is 0 0.5 into 20 is 10. So 10 plus iron loss plus 0.25 copper loss is equal to 10 divided by 0.98. So if we, the second equation we will be getting from here. So this comes out to be 10 divided by 0.98 minus 10. So it is 0.2041 kind of. This is your second equation. So from these two equations you can calculate the copper loss, right? So just subtract 1 from 2. We'll be getting 0.75, sorry, so 0.75 into WCU is equal to minus 0.40816. So it is coming out to be 0.2041. So the copper loss that is coming up is 0.272. This is in terms of kilowatts, right? So now that we have the copper loss, we can calculate. So the percentage equivalent resistance, for this we need to calculate the per unit resistance. So we know copper loss is equal to I square R, right? So if we convert all of this into per unit and calculate and equate it, so for we have got, this is the total copper loss. So if we write it in terms of per unit, it will be 0.272 divided by the rated power of the transformer, which is given as 20 kVA. So this is just calculating W copper per unit equal to I square. This will be the rated one, rated voltage, times RCU. We are just putting it here. So this will be equal to, now whatever the rated load, we are just dividing it, so it will be the 1, right? Whatever the current here is, that is the rated current, so it is 1. R, we will get it in terms of per unit, because I guess you have seen in the lecture that in like the resistance per unit is given by whatever the equivalent resistance is divided by the rated impedance, which is termed as the base impedance. So we are getting this RPU from this equation. So if we simply calculate RPU, that is per unit, it comes out to be 0.272 divided by 20. So it is 0.0136. Now we have to calculate, this is our per unit you have got, we have to calculate it in terms of percentage. So percentage RPU will be this into 100, so it is 1.36%, which is equal to option B. Everyone got this one? Anything to ask? If not, then we'll move to the next. Yes.
How we took that I as 1, madam?
So whatever the rated load, like here the current is, let's say when we calculate the current here, so it will be like 20 divided by, if we calculate as the equivalent on the high voltage side, so it will be, suppose 20 minus 20 kilovolt, sorry, 10 cube by 2500, it will come out to be some I value. This is the rated.
Okay, okay.
So since it is occurring at the full load, that same current, like since we are calculating per unit, right? So
Yes.
this will be divided by this. So that will come out to be 1, because it is at the rated current itself. So in per
Okay.
unit, the value is divided by, in case of resistance, it is called as the base impedance. In case of like the power, it is divided by the rated power. Whatever the value is divided by the rated magnitude, right? So in
Okay.
this
Yes.
case, it will be the whatever the rated current divided by the rated current, it will be 1. So it is 1 square.
Okay,
Sorry.
ma'am. Yeah.
Okay. Any other question?
Nothing, ma'am.
Okay.
We'll proceed.
Okay. Then we'll move to the next question. The next question is again about related to the efficiency of the transformer. However, in this case, uh, first a single phase transformer with, like, the two winding transformer is, the specification of a two winding transformer is given, which is rated at 50 kVA with the low, this is the low voltage side, this is the high voltage side, which has an efficiency of 95% at full load and unity power factor, that is x equal to 1, cos phi is also equal to 1. Now it is reconnected as an auto transformer. So now the low voltage side, like uh, it is, let's draw the auto transformer first, so that we will know what to calculate. So if it is again reconnected as an auto transformer, and we have to find its efficiency at its new rated load and unity power factor. So new rated load means the current uh, that is there for this auto transformer at unity power factor. So just let us draw it first, then we will see. So we have 500, that is low voltage side on this side and high voltage side on the secondary. So initially, uh, I'll take just a different color. Just hold on. Initially, it was a two-winding transformer in which there was one primary winding and the other one was the secondary winding. But now it has been connected into an auto transformer. So if initially this was the current at the here it was low voltage, okay, so at the low voltage side, and in this case if the current in the secondary was at the high voltage, like if IL was the current at the high voltage side, this total current of the auto transformer, let's denote it by IA, it will be the summation of these two. Sir had shown in his lecture reverse case, like this one is uh, a kind of step up auto transformer, but sir has shown for the higher voltage side on the primary and the lower voltage side on the secondary. Similarly here, the current in the auto transformer will be a summation of these two. So basically we need to find first the low voltage and high voltage side current from the previous connection, which is given here. So how will you find the low voltage current, which is it will be equal to the rated power that is given, 50 kilovolt ampere divided by the voltage on the low voltage side. So it is 250. So it is basically 1000 by 5, that is 200 ampere. So this is equal to 200 ampere. Similarly, in order to calculate the high voltage side current, it will be the rated power divided by 500, right? So it will be 100 ampere. So now that we have for the auto transformer, we can calculate this rated current. So for this, the current will be 200 plus 300. Sorry, 200 plus 100. That is equal to 300. Yeah. Now we have the rated current in the primary side, and we also have the voltage. So we can calculate the power rating, right? So if we are to calculate P, it will be V into I in kilovolt ampere. We can calculate this. So the total power. So in case of in order to calculate the efficiency, we also so for the auto transformer, if we are to calculate the efficiency, it would need whatever the rated at whichever rated current it is operating, whichever rated load it is operating, times Vi cos phi x Vi cos phi plus copper loss and current core loss, right? So just consider it is the same transformer that we had before, only the type of connection has changed. So whatever the copper loss was there before, since it is both of them are having the same number of windings, so the core loss and the copper loss will remain the same because the number of windings have not changed. It is just the configuration that has changed, that we have tapped it into the winding and converted it to auto transformer. So we are just approximating this part like to be just the total loss. If we since we already have the efficiency of the previous connection of the transformer, we can calculate the loss, because the unknown quantity right now we have is the loss part, because we have the current, the voltage, and it is given it is running at unity power factor. So since it is given, it is efficiency at its new rated load. So new rated load here is 300 and it is performing at full load. So X will be equal to 1. So all we have left is this loss part. So from the previous connection, let us calculate this loss. So we have efficiency, which is equal to 0.95. It is equal to the volt ampere rating is 50. Let us keep this in kilo units only, like 10 to the power 3. So it is 50 plus, let us denote this both this as P loss, right? Because the previous connection was also performing at the rated load. So X will be equal to 1. So anyway, it will be just the total WCU and the Wi, which are the copper loss and core loss. So let us write it in terms of as P loss. So P loss, if we just the total loss, if we just calculate, it will be 50 by 0.95 minus 50. So let us calculate this. 50 divided by 0.95. It is 52.63.
61.
Sorry.
52.631, ma'am.
Right. So the total loss is 2.6316
Yeah. 2.4.
in units of 10 to the power 3, that is kilowatt, right? So now we can now calculate the efficiency. Now that we know the loss, we can calculate the efficiency of the auto transformer, right? So it
Yeah.
will be the efficiency of the auto transformer will be X is 1. So we have so let us calculate VI. Voltage is 500. Current is we have calculated here. Current is 300. So it is 15 four zeros, that is 150 kVA, right? So for the auto transformer we can calculate now. So it is X is 1, rating is 150, it is operating at unity power factor, 1 into 150 into 1 plus the losses. So it is 2.6316. Just calculate this one, 150 by 150 plus 2.6316.
98.27.
Right. So it is 98.27% efficiency. This, the option A. So I hope this is clear. If yes, we can move to the next question.
Yes.
Okay. So for the next question, uh, the it is given for a single phase transformer, and it has the turn ratio is given. Turn ratio is primary winding by secondary winding N2, which is also denoted by K. It's given as 4. The resistance this and the reactance this and this are for the high voltage and the low voltage windings respectively. What we have to find is the voltage that needs to be applied to the high voltage side in order to obtain the full load current of 200 ampere on the low voltage winding on short circuit. So we have earlier seen that in case when the transformer short circuit test is done on the transformer, we basically neglect the core losses and we calculate the copper losses, right? Because the
Yes, ma'am.
core losses becomes almost negligible and it can be neglected. So in this case, initially the winding of the transformer would be somewhat like this. So the resistance and the reactance on the secondary, and this will be the load current that will be flowing here, and this will be the input voltage which we need to calculate. Now in this case, since the turns ratio is 4, that is it is greater than 1, so this is the low voltage side and this is the high voltage side, right? So in order to compute this, let us first convert all the secondary voltage to as a equivalent primary, the secondary reactance and resistance, we transform it with respect to secondary to primary. So we have to calculate R2 dash and X2 dash, right? R like for both these cases, when the secondary resistance is calculated in terms of the primary resistance, we have to divide or multiply by the turns ratio. Can anyone tell? You haven't taught this one, right?
Into K square.
Yes. So we have to multiply by the turns ratio. So it will be K square times R2. Similarly, the reactance will be the same, X2. So K square is 16 into R2 is given as 0.045. So R2 equivalent will be 16 into 0.045. 0.72. Similarly, x, sorry, I don't know why did I write the square? Let me remove it.
Dash.
Yeah. So x2 is again 16 into the reactance is given as 0.25. So 16 into 0.25, which comes out to be 4. So the new circuit now will be, it will contain the primary resistance and reactance and the equivalent secondary resistance and reactance. So so this will be the equivalent circuit neglecting the core losses. So we now have to find this V input. So this is R1, X1, R2 dash, X2 dash. Now the rated short circuit current that is flowing here, ISC, we also this short circuit current, this short circuit is done on the high voltage side here, so we need to convert it and find the current in the low voltage side. So for current it will be, let us calculate the equivalent RSC dash. So in case of current it gets divided, right, because
Yes.
it is in the
Yes, sir.
reverse ratio of the turns ratio. So the current that is given is 200 ampere divided by 16, which is actually like ISC by K. So divided by 16,
12.4.
right. Sorry, it won't be 16, it is divided by K, right? Not K square. So K is 4. Sorry. So it is 50 ampere. So this current is the current that is flowing in this particular circuit. So this is ISC and it is 50 ampere. Angle is 0 degree because there is uh, no other J component here. Now, in order to calculate V in, what we need is I into Z, right? So let us calculate the equivalent Z. So Z is equal to the R1, which is given as 0.9, plus R2 dash, which is 0.72, plus J into the given primary reactance is 5 and R2 dash is 4. So it is 0.9 plus 0.72. So it is 1.62 plus 9J.
9.
So if we simply calculate the magnitude, it will be square square root of 1.62 square plus 9 square, right?
9.144.
Okay. So it is 9.144 and the angle of Z will be,
Tan inverse of 9 by 1.6.
right. So it is 79.92. So now you can calculate V in, right? So V in will be 50, angle is 0, Z is 9.144, angle is 79.92. So 50 into 9.144. This comes out to be 457 0.2, angle is 79.92. So in the option C kind of falls within, the answer comes for within the range of what is given in option C. So option C is the correct answer. So everyone got this one?
Yes, ma'am.
Okay. So this was the last question given in the previous rolled out assignment of transformer. The next question comes of induction motor. So this is a very basic question of the induction motor, in which it is given that it is a uh, motor with 10 pole with 50 hertz is the input frequency, and it is operating at a speed of 590 rpm. This 590 rpm is basically the rotor speed. So in case of induction motor, uh, the rotor rotates at a slightly lesser frequency than that of the uh, magnetic field that gets induced in the in this that because of the current supply to the stator. So it cuts to the flux, cuts to the conductors of this stator, and thereby EMF is generated. So the if there is there is slight difference in the frequency of the rotation of this rotor with respect to the synchronous speed of the stator, so that this EMF is not equal to 0. That is how this motor operates. So in the question, when it is given that it is operating at a speed of 590 rpm, it suggests that it is the rotor frequency. So we have to find the speed at which the magnetic field of the rotor rotates with respect to the stationary observer. Stationary observer means someone who is observing from outside. So basically you need to calculate the speed of this, the frequency of this synchronous, basically you have to calculate the synchronous field, right? That is,
Yes.
will be equal to the,
And 120 F by P.
right. It is given as 120 F by P.
F
F denotes this
600.
frequency, that is given 50 hertz. So it is pretty straightforward, into 50, and P is given here as 10 pole. So it is 600. So this is the correct option D. So you see, there is a slight difference between the rotor and the stator speed.
Yes.
Similarly, in the next question, it is given that a grid connected operation of a three-phase induction motor which has 6 pole operating at 50 hertz. The speed of the machine is observed to be 1003 rpm. Neglect all the losses in the machine. We have to find which statement is the correct option for this. So for this, let us calculate the this is the uh, frequency of the rotor speed, right? So for the stator, let's find out the synchronous speed, as we have seen in the earliest problem, 120 F by P. So it is 120, frequency is 50 hertz, and it is a 6 pole machine, so 20,
1000.
so it is 1000. Now you see, in induction motor, the rotor speed is less than that of the stator, right?
Yes, ma'am.
But in
NS
this
is
case,
greater than NI.
however, in this case, we see that the rotor speed is greater than the stator speed, which denotes that this is a generator.
Yes.
So this is basically generating the power. So now among this option, we have to find which is correct. So the machine takes active power from the grid but delivers lagging reactive power. It cannot be. It is a generator, so it has to deliver active power. So this option says that it delivers both active and lagging reactive power to the grid. So in case of, I'll just say, in case of a generator, like synchronous generator specifically, a prime mover, it drives the rotor speed above the synchronous speed. That is why we get this relation. And because of this, like, the stator flux induces the current in the rotor, but there is an opposing rotor flux which is also now again cutting the stator. So these current that is induced in the stator, it is actually lagging behind by 270 degree from the magnetizing current, and it is in phase with the magnetizing voltage. So basically the generator will always deliver real power to the power system. It can never deliver reactive power. So now in order to see how it takes the power from the grid, so in case of a standalone system, capacitor bank is connected to the machine, but in case of when the motor is connected to the grid, it actually draws the reactive power from the grid in order to maintain the air gap flux. That is there is a the it maintains the flux in between the stator and rotor, the which is known as the air gap, right? There is a small gap between the rotor and the stator. So in this case, the only option that matches is the machine delivers active power to the grid and takes lagging reactive power from the grid. So the correct option is option D. Is it okay? Is it okay to you all? I mean, if you read the I don't think the synchronous generator has been taught in detail yet. So
Yes.
yeah, once you get to the working, you will get more feel of it. If you have any question, you can ask. Otherwise, we can move to the next question. It is
Ma'am,
basically
if
yes,
NS is greater than NR, it acts like motor, induction motor, right, ma'am?
yes.
Then
In case
it delivers,
the
uh,
rotor frequency is slightly less than the stator frequency, then it acts as
yes,
a motor.
yes.
But in the reverse case, it acts as a generator. That is, it supplies power.
When it acts as the motor, it delivers. What happens to the grid, ma'am? When it acts as a motor?
So in that case, like motor is what, like in case of generator, the mechanical energy is converted to electrical energy. So this
Yes,
question of supplying power comes in case of generator. In motor, it will uh, you know it will act on a load, like that is why you have seen in case of like it will, like motor basically rotates that power, it like the mechanic, it converts it into the mechanical power, right?
yes,
The generator supplies it, motor does not, right? It
yes, ma'am.
consumes.
Yes, ma'am.
Okay, anything else?
Nothing.
Okay, then let's move to the next question. Again, in here it is about an induction machine which has a which is operated at a speed of 1400 rpm. This is the rotor speed, and the rotor EMF makes a 2 cycle per second. Now, in case of the in case of induction motor, so the rotor, like as we have seen earlier, the rotor speed is a little bit lesser than the stator speed, right? So
Yes,
uh, the EMF that is getting induced in the rotor because of because when the magnetic field, like it cuts into the like the
conductor.
rotor conductors. So let us say like ns is the synchronous speed of the stator and n is the speed of the rotor. So the total induced UMF is given by uh, so this is 120 F by P. This is the net difference in the stator and the rotor speed, and the EMF that is getting induced. This frequency is actually frequency of the induced voltage or current, whatever be it be. The frequency of this is in relation with the difference in speed of the rotor and the stator. Sir has explained this in his lecture once. So if you can recall, the frequency of the induced EMF or voltage is given as, suppose if it is F, it is given as Ns minus the rotor speed. Do you remember this?
Yes.
Yeah. So if this formula is kind of rearranged, so like Ns minus N by, let us divide by Ns. So this is, let's say, like, let this be. So we will also, so Ns we we can cancel 120. So no, let me write it in another way. So wait. So a term called slip has been introduced to you in the lecture, which has a relation with the rotor and stator speed as ns minus n by,
Minus NR by NR.
right.
NR. Sorry.
So this is known as slip.
Yes.
And we have like the in the previous we have seen this stator speed can be calculated 120 f by p, where this is the supply frequency, right?
Yes.
So if we write this, so let us take all of it on this side. Let f be the, this is the, uh, let us write it in term, let us denote it by fe. So ns minus n equal to 120 by p. Fe is the, fe is because of the frequency of the induced EMF or voltage. So let us take rest of the term on the other side. So fe is equal to ns minus n p by 120. So let us, if we substitute p120 from here, we will get 1, if we write p by 120, it is equal to f by ns, right? So ns minus n into f by ns, and this part is known as the slip, right? So it is s into f. So the induced EMF, the frequency of the induced current or voltage is given as slip times the input frequency. Here this input frequency is 50 Hertz. So this is the relation that we are going to use in this problem. So we are given that the rotor EMF takes 2 cycles per second. That is, its frequency is given as 2. Slip is what we do not know, and the input frequency is given as 50. So we can calculate slip as 2 by 50, right? Which is equal to 0.04. Now the same machine, when connected to a balanced three-phase at 60 Hz supply, rotates at 1720 RPM. So for the next case, uh, let me just go to the next page. So for this particular, sorry, yeah. So for this next case, we have the supply frequency and the rotor speed, and we can calculate like the slip from here, right? So we do not know ns for this particular, uh, for the second case. We have, for the first case we have, uh, we we can so for the first case, let us calculate ns first. So now that we have the value of sleep as 0.04, we can put it in this equation. So it is ns minus n by n equal to 0.04. So it is basically 1 minus n by ns, 0.04.
Ma'am,
Yes,
can't we calculate NS directly with 120 F by P?
uh, the p is not given here, right?
54. Okay.
P is not given here, so that is why we had to go through calculation of sleep.
Okay.
Yeah, so it is n by ns is equal to 1 minus 0.04. So ns will be equal to, n is given as 1440 by 1 minus 0.04. So let us just calculate ns. 1440 divided by 1 minus 0.04, which is 1500 rpm. Okay, now let us go to, so let us denote, since when it is for case 1, when it is operating at 50 hertz, right? So ns1 was 1500 rpm. Now in the second case, it is operating at 60 hertz. So like you were saying, if we try to calculate ns, which is 120, so f by p. Now like we do, since we do not have p, this is the new frequency, that is 60 hertz. Since we do not have p, we can just like write it in terms of so we have ns1 here, it is 1500, which is again 120 f1 by p. This f1 is 50 hertz, right?
Yes.
So we can just equate it to this one. So let us write 120 f1 by p. So we divide by f1 into f2. So this particular thing only we are multiplying numerator and denominator by f1. Okay. So this is actually ns which we have, right? So ns is 1500. f2 is 60, that is the new frequency, and the old frequency is 50. So we can calculate the synchronous speed of the second case where it is connected to a 60 hertz supply. So it is 1500 into 60 by 50. It comes out to be 1800.
1800.
Now, why do we need to calculate this ns2? Let us denote this by ns2. Why do we need it? Because we need to find the frequency of the current induced in the rotor circuit. So similarly in the previous equation, so we also have to calculate slip, because in order to calculate the frequency of the induced current, we need to find S into F, right? This is the sleep, and this F is actually the frequency of the supply, which is 60 hertz in case of in the second case. So in order to calculate sleep, we need ns minus n by, so I'll just write it as 2, ns2. So this is for the case 2. This is the synchronous speed. We have calculated it as 1800. The N2, which is the rotor speed in the second case, is 1720 by 1800. This comes out to be 1800 minus 1720 divided by 1800, which is 0.044. So the new frequency of the induced current in the rotor circuit will be 0.044 into 60. which comes out to be 2.667, which is option A. Is it okay?
Yes, ma'am.
Okay. So these were the six questions left. The other six has been done by my colleague. So the next part of the induction motor and will be covered in the next interaction session. Uh, so in the previous, the ninth quiz, a lot of people have uh, queried, like mailed me about the solution of like the quiz 9, which has not been uploaded in the I mean website yet. So from the NPTEL team, they have said, like, if you have any queries, you can directly put the questions in the discussion forum, and they will reply it to that until like they upload it in the website. As we receive the maximum number of queries for this particular question, we will solve this one. So it is given that a three-phase load is connected to a three-phase balance supply, and all the impedances are marked in ohm. The line-to-line voltages are given, and it is given that the current in the neutral wire is 0. That is, current here is 0. We have to find the unknown value R. So we have done a similar kind of problem in our ninth interaction session. So here we will apply KCL at this particular node, that is IA plus IB plus IC are equal to 0. Since the line voltages are given, we can calculate the phase voltages by dividing it by root 3, right? So in each case it is 440 divided by root 3. So if we write IA in terms of minus IB plus IC, so it is VAN by R minus of VBN by R plus VCN by R. Now in each of this case, the magnitude are all 440 by root 3, right? So we will just not write it in terms on by r. The magnitude will get cancelled on both the sides, right? So let us write this one is angle 30 degree, in this case minus of, sorry, it will be like in this case it will be XC and XL, right? So VBN, the angle is minus 90 degree, and it is J10. In the capacitance, it is angle is 150 degree by minus J10. Since we have to add, let us write it in terms of J. So it is minus cos of 90 degree will be equal to 0, and sine of 90 degree is minus, sine of minus 90 degree is minus J. J10 plus root 3 by 2 J half. Sine of 90 degree, sine of 150 is half by minus J10. If we bring the minus sign inside, J by J10, so it will be root 3 by 2 times of, there will be a negative sign here, so it is J10 plus J by 2 times of J10. So 1 by 10 minus of root 3 by 2 into 10. Now if we multiply numerator and denominator both by j, so it will be j, and here it will come minus 1, and it is 1 by 20. So if we just take 1 by 10 common, it is 1 plus so this minus 1 and this minus will become plus, so it is root 3 by 2 into j plus half, right? So it is 1 by 10, 3 by 2 plus root 3 by 2 times j. Now if we take root 3 common, it is root 3 by 10 into root 3 by 2 plus half of j. Now, so we have the magnitude to be root 3 by 10 and the angle to be, so when we have like cos of when the angle is 30 degree, so cos 30 is root 3 by 2 and sine 30 is half. So this angle is, this is the magnitude and this is the angle. So if we compare with the value of r that we have, so this was the right hand side of the equation. So when we compare this, we find that the value of r is root 3 by 10, right? So r is, 1 by r is root 3 by 10. So r is equal to 10 by root 3, which comes out to be 5.77 kind of 5.77, which falls in this particular range in option C. So option C is the correct answer. So for as for the rest of the question, if you have any more doubts, please write it in the discussion forum, and there will be response to that. Instead of like each of one of you mailing individually, it will be better if like you post it in the forum so that everybody can see it. Thank you for today. We'll meet in the next interaction session.